Hi, I'm Frédéric Simonis. So I'm, as mentioned before, I'm one of the core library maintainers of preCICE, and I kind of traditionally give this talk where I show you a bit around about the newest releases and so on, at least what happens inside preCICE itself. So tooling and a little bit of tooling, but the ecosystems part comes later. Yeah. So let me start with not the release, but release strategy. Yeah, we needed internally also in the team some kind of predictability when the next releases come out. So we kind of sat down and figured out a release strategy where we can release twice a year, which is frequent enough for us and also stable enough for the user side. And what we come up with is this spring release that we do in March, April, and autumn release that we do in September, October. And important here is also that bug fixes are always allowed. Right? So this is something we always keep open. And so general idea is that we always have a feature freeze on March the 20th. This gives us time to prepare the release itself and also start porting bindings and adapters and all of that stuff and test this. And then release as soon as possible in April. So this year it was actually the 1st of April, which is kind of funny, but yeah, anyways. Yeah. Yeah, and the same for September, October. So we start the feature freeze on September 20th, so this is very soon. And then also release early October. So the idea here is also that we take some of the feedback and maybe also bugs that we figure out here during the workshop and then fix those, and so we can also release those then in a pretty timely manner. In terms of a timeline, here you see the releases of the version 3 family. So this was, most of it was early 2024. So here we already had an April release, funnily enough, some bug fix releases afterwards. Then the last big release, the 3.2, was in April, as I mentioned, April 1st. And now the next one will hopefully be very early October 25. We shall see. This brings me to the spring release. So this was a pretty feature-heavy release. So the next release that we'll see, the autumn release, will be not so feature-heavy, but this has a lot of content to it. So let's start with something. We're struggling with some very tedious problems in preCICE. That is, some issues were very hard to understand and debug, and it was still very easy for even very experienced developers and users to run into this. And one of them here is for mixing configuration files. And this can very easily happen if you run on distributed systems and maybe even on completely split systems for different participants and so on. And you still need to figure out where your configuration files are located and need them in sync, to keep them in sync. And sometimes this is very obvious, but sometimes it isn't. For example, we had a case where we had two simulations where two participants were running nearly exact same configuration files, but the one was using a serial coupling scheme and the other a parallel coupling scheme. And to debug something like this is sometimes, very problematic. Right? And so now we added additional checks in preCICE. So we are now ensuring that the configuration file content, at least, is identical on both sides. Then the next one, which is similar to this, is mixing preCICE versions. Right? So we always allowed mixing different versions of preCICE, even though we never supported it. And now we enforce that they are the same. And the important part here is that this is versions, not configurations. So you can still build one preCICE without MPI and another preCICE with the specific boost and eigen that your solver requires. So this is all fine. You can mix different configurations. The connection interface on the network backend is stable. That's the most important part. But we do not guarantee intercompatibility between versions. So this is something we now also fix and locked down in preCICE. And the last part is, when people start mixing very wildly, very wild directory configurations. It can get very confusing sometimes where your participant is running, what the working directory is, what's the relative path resolved to, especially in terms of configuration, etc. And this is why we now also print like the working directory, the absolute path to the working directory, which can be huge on clusters, but that's not an issue, as well as the full path to the configuration file in the preCICE hello statement that you normally see when you start preCICE. So this is also super valuable for you, as you can later check, as well as for us, so we can quickly have a look at this too. And we know that some people use this as workarounds. So our stance here is we forbid this now, so if you need this still to get some specific case running, contact us and we work out a real solution. And people that use these things will know. Something else that we have finally introduced are exceptions. That sounds pretty boring, but it's actually pretty exciting, at least for us. So the stance in preCICE was always that errors are unrecoverable, right? From a coupling perspective, this makes no sense. If you if you do like a time step to infinity or so, what is this supposed to mean, right? So currently the stance was always to call standard abort. So preCICE throws an error. You see this on the shell or your log file, whatever, and then it calls abort. Of course, this is very ugly in terms of cleaning up. So now we went to an exception way of handling this. So now we throw a preCICE error which contains the error message. So you can also use this later in your adapter and pack it in your own logging framework if you want to. This has some upsides. So first of all adapters can clean up now, finally, which especially on HPC systems is kind of nice. And interactive sessions such as Jupyter notebooks and things like Python interpreter, IPython, and so on, they don't crash, right? So you can just continue using preCICE, even though it may be in a bit of a weird state. So what happens after an error is still a bit unclear. So we're trying to lock this down more and more, but this takes some effort. And the big upside of this is that we can finally test expected errors. So we can now test what happens. So errors that happen in very specific cases, we can reproduce the cases and also explicitly check for the error to be raised. Sounds boring, but it's pretty important for usability, right? If you're using the convenience header, then you don't have to do anything. Everything will be pretty much transparent to you. Another part is that we generalize the API access. So for people that use direct mesh access, you know that in the receive mesh tag, you have to specify this direct access and say that set as to true, right? We now renamed this. Now we call this API access to make it a bit more general. This is still backwards compatible till version 4. Afterwards, we'll remove this. But so if you're using the direct access version, don't worry, it will stick around. And this makes it more general in terms of wording for both the direct mesh access using read and write, as well as just-in-time mappings, which I'll come to in a minute. And the other part is that we also now allow setting these mesh access regions for multiple meshes. This is also an open to-do. So what are these just-in-time mappings? I hope you can read this in the back. If not, then you're out of luck. So if you now have here your configuration, where you receive a mesh with the name M here, and you say, okay, I would like to have API access to this mesh, then you can define mappings, so read mappings from this mesh or write mappings to that mesh without a counterpart, right? And these are what we now call just-in-time mappings. So currently, you cannot define all kinds of meshes, also mappings. It's constrained to some. We'll add more in the future, but this is like to get you started. And this allows you to do something like this. So here you have like an arbitrary particle code here. You set your mesh access region, which you need for the API access anyways. Then you initialize, and in the coupling loop, you do not, like in the direct mesh access that we have before, you don't read positions and vertex IDs that you can then read and write to or from. But what you now do is you can tell preCICE, here I have positions, please map data to these positions and return like the data to me. Right? So this is the first section here that's highlighted. Oh, I haven't highlighted here. So this section here. And then you can use this in your solver, then you get some results, and then you can also kind of do the same. But say preCICE here, I have positions and data that relies on these positions. Please write this data and then map it to the remote or received mesh, or the directly accessed mesh. And one this you can find in the poster by David Schneider on flexible mesh particle coupling with preCICE in the poster session. Something that sounds pretty minor but can be useful in some instances is that these projection mappings are, by nature, pretty sensitive to meshing and partitioning changes, right? Because we map to the nearest elements and partitioning loses some of these elements and so on. So currently you see this mapping distance, which gives you an information how far the mapped or the projected point is away from the source point. This gives you a good idea about like the extrema, but doesn't give you a good idea about what is actually happening. So we have now something that looks very trivial, but it can be very helpful. So in this case here, you see that also what elements the this projection mapping selected in the computation process of the mesh. Next up is mappings on GPUs, again by a feature from David Schneider in collaboration with Timo Schrader. This paper at the bottom here is actually a bit old, but it's still relevant for this. So now you can use, then I can run global direct map, RBF global direct mappings on GPUs. So either going with CUDA or HIP. Here we use, in general, we use now Cocos for the hardware handling and Gecko for the high-level solvers. And in this case, we also use NVIDIA CUDA, so QBLAS, and AMD HIPLAS for the QR decomposition. There's also support for Intel, at least coming, or let's say in the work, so using SYCL, but it's still on the horizon. So yeah, so check out the paper if you want to know more. This is in a coupled paper. Next up is a feature from Benjamin Rodenberg. So he is now here for some reason, but yeah. So this is the dissertation from him in case you want to read up on this. So before version 3, you always had constant data in your time window, which you can see here. So this is like a complete time window, right, with big delta T, giving you the time window size. And here you have two solvers. So on the left-hand side, you have a solver that does 2 time steps. So the little delta T is here the time step. And on the right, you have a solver that does multiple small time steps. So in the second iteration of an implicit coupling scheme, you would then, at least in preCICE version 2, you would only have access to the last, to the end sample, essentially. So we had like a constant view on the data. This was version 2. In version 3, Benjamin added this way of having higher order interpolants and so on and so forth. And what you can then get out of this without any further changes is that you now have a linear interpolation between the end and the beginning sample of your time window. So if you read, you get actually the linear interpolant between these two. And this was the default behavior. You can enable substeps, then you get a more intricate interpolant that also takes into account these intermediate samples here. But the problem was back in version 3 and up to now, we always had the issue that this was not supported by all acceleration schemes, and we didn't want to end up in a very strange situation where some things would break, and so we tried to leave the default safe. So we left the substeps off, and this is what you get essentially without touching anything. Now in version 3.2, we finally were able to enable substeps by default. So what you now get without changing anything is in this situation here that you get a piecewise linear interpolant, where essentially the idea of a sample is that if you write data and then call advance, you produce a sample, and the advance dt gives preCICE the information where this sample lives in time, right? And now you can actually go to the data in your configuration and crank up the waveform degree to, let's say, second order, and then you get something like this, and you can then create interpolants of higher orders, which then require, in this case, as an amount of samples for the n samples for an nth order. Yeah, and if you have more questions about this, you can have a structured read by looking at the dissertation, or an unstructured conversation with Benjamin, who is also here. Okay, and this leads us to acceleration. And the acceleration part is, the first part here is very important. So we have finally support for substeps in Aitken and quasi-Newton acceleration. So this was the missing link to enabling this by default, at least for implicit coupling schemes. Another part here is also that we finally, with the work of Jun Chen, finally took the QR3 filter that we proposed in a paper in 2022 and integrated this in preCICE. And so this has some interesting properties, which are that it recomputes like the QR decomposition only when like columns are deleted, which is like an efficiency improvement, right, over the current situation. And we support now secondary data in the IQN IMVJ. So that's data that is not used for the coefficients, but it is still accelerated. This leads us to some defaults that changed. So the IQN filters now default to QR3 because of the efficiency gains. And in Aitken, we now default to an initial relaxation factor of 0.5. And the important part here is that now you can essentially use all the different acceleration schemes without touching the parameters. So essentially you just say, these are the, either you say nothing, you don't need to specify any additional parameters, or you say, this is the data I want to use to compute my my factors, essentially. Regarding the first step here, the quasi-Newton on support for substeps, this was actually quite an undertaking, and there will be a talk about this by Philip Birken. And Nicolas also spent a lot of time to integrate this in preCICE. So it's nice to see that this ends up in a talk here at the workshop. This leads me to runtime remeshing. This is a feature that I've been working on for quite some time, and we finally have a prototype in preCICE that actually works for some narrow cases. So to use this, you need to turn experimental features on in the configuration file, and also specify that you want to allow remeshing. This does a few things. It mainly narrows down your configuration to a single coupling scheme, which needs to be parallel. So a parallel implicit or parallel explicit coupling scheme. And with this, you can do something fancy like this. So in your coupling loop, when you read data, you can now evaluate your own criteria and say, okay, let's say the red data are vertex displacement and my mesh is now, for example, degenerate or so, then I may need to do runtime remeshing at runtime, which is just one example. So at this point, you can then do the remeshing, you get new positions, And you can say to preCICE, preCICE, please throw away my old mesh, and I define new vertices, and then continue with my solve. And I then can write data to these new IDs of these new vertices, and preCICE then handles everything else seamlessly in the back. Right? So that's kind of the design of this API, to be as seamless as possible. Of course, you see that the data you read here and the data you write are on different spatial locations, so this is something that you need to figure out. This is adapter dependent. There are multiple ways of solving this, but this is essentially a limitation from preCICE. There will be a talk about this tomorrow, given by me. Yeah. Then we did also some changes in the prefiling, also the profiling backend. So we now track most API calls. It's like read data and write data and so on. So for read data, this is especially interesting as we now do the sampling of the interpolants, which can become costly and maybe interesting to study what the overhead is here. And we track some things that can get expensive if you go into like volume coupling territory with multiple millions of cell points and so on, such as exports and watch points and so on. Also a feature that is useful for adapter developers is that you can now specify your own profiling sections in your adapter, and these will be then nested under the solver advance. These can also be nested if you want more details there, and you can also mix these with the API tracking before. So if you now call, for example, read data inside this, the read data also will be nested. And this will then be seen in the cleaner output here. So you will see then in solver advanced, it has like this sub-events here. In this case, the solve. Then something that is very technical, but I'll mention it because it is something that early adopters of substeps will have run into, is that with the version 3.2, we disabled the so-called Nagel algorithm in the sockets backend. So if you then exchange multiple substeps, we had the issue that some of these exchanges were blocking, and blocking in this case was very blocking, and it led to led to the Nagel's algorithm kicking in and essentially leading to a lot of delay inside this exchange of substeps and so on. So the more meshes you exchange, the more costly this becomes. And we saw a big change, especially even in the tests that we had. So if you're an early adopter and use sockets for M2N, please make sure that you upgrade to version 3.2. It will make a difference. In terms of platform support, we are now also actively testing Intel MPI, as well as the OneAPI compilers from Intel, so C, the C++, and the Fortran. And we moved the baseline, as we normally do, from version 20.04 of Ubuntu to 22.04. We also have some compatibility fixes with Boost Azure. And yeah, so we also now require Ginkgo 1.8 and higher, and Cocos version for 1 point higher, which shouldn't be that much of a problem. This leads me to the autumn release, which I said will be a bit smaller in scope. So here we try to fix some bugs that we run into, and we also did some introspection on the error messages and especially like the log output that you see on a common basic as a user, which sometimes can get a bit lost from a developer perspective. And we start here with the coupling state. This is something you'll see, or you've seen a lot probably during the course. This is whenever you call advance, preCICE will tell you in an info statement how the coupling looks like that's at the end of the advance call. And so we cleaned this up a bit. So now you have, now for explicit coupling, we don't mention iterations anymore because they don't exist. And we removed some things that were implied by, in implicit case, iterations and time windows, cleaned it up a little bit, and refer to common abbreviations. right? Like it for iterations and so on. So the goal here was to make this more compact and to reduce noise. And one of the big drivers for this is that compositional schemes where you have multiple coupling schemes in one configuration and one participant takes part in multiple coupling schemes leads to something that we call a compositional coupling scheme. And so this participant then prints out multiple of these in one go, which can be super confusing. And yeah, so what we do now is we have a very neat output here. We also went over some of the actions messages that you get. So the actions was a very old interface that we also renewed, and we forgot to look at some of the error messages. So if you now, for example, don't check if read checkpoint, so if you need to write a read checkpoint and you use an implicit coupling scheme, then we assume that your adapter is not ready to do implicit coupling, and you get an error. And up to now, you got like a super cryptic message, and we went through this, and you get now a very specific message with exactly what is most likely the reason why you got this in the first place. So this is just nicer from a user standpoint. Another use case here that is also some people run into, this is a bit niche, but still important. You can compile preCICE without MPI support. So in this case, you also use socket communication for the inter-participant communication. So if you have like a solver that runs on multiple processes, preCICE will handle communication between the different ranks, or ranks in this case, but processes using TCP/IP. If you do this, and so far, if you have on the left here the solid participant, if you run this in parallel, it will complain that you need to specify an intra-communicator, which you don't need to do with MPI. If you now add this intercommunicator, like in the fluid here, and you run this in serial, it will complain that you added an intercommunicator even though you're running in serial. So this is something we never really run into until a user did, and this is something we fix now. For the fluid, this is easy, we just ignore it. On the other hand, it's a bit more tricky because you need to normally specify like interfaces and so on. So for the default, we now default to an socket interface on the loopback device. In terms of platform support, this could be interesting for some of you. We have now had a long discussion with the package maintainer of the MySys2 package of preCICE, so the one that compiles on Windows. Some things were broken. We never knew. They told us about this, and so we were actually not only able to fix it, but we now also actively test compiling preCICE on Windows using MySys2. And we also use for this specific case the Microsoft MPI version 10.1.1 because the later versions are all broken for some reason, and the WinSox via Boost Azure. We also had to do some compatibility works with libxml2, which now supports 2.14 plus, and Boost, which now supports 189 plus, which both don't use semantic versioning for also some reason. And part of the discussion with the Windows people is that it turns out that the static build of preCICE was broken still since version 3. So actually before this as well, during the complete development time. So we know that for the last 3 years, no one used this. So we now finally pulled the plug on this and reduced confusion by just making it always build a shared library. In terms of profiling, we also took one step back from last time. We moved all non-steering API calls into a new API mode. So in profiling, you can define the mode here. Non-steering means everything except of the constructor, initialize, advance, and finalize. These things are important for you to evaluate like the coupling overhead in general. So these are still part of the fundamental APIs. Also the fundamental mode. The rest of the API moved into the API part, which can still be interesting, but can lead to a lot of unnecessary bulk in terms of profiling files and so on. We also changed the formats that the ranks write to a more space-efficient one. So we write a TXT-based format that's also easier to parse. The current JSON formats were a quick fix that didn't really scale well. And we, for very big cases, which mostly goes into in the development territory, you can also now enable compression of these profiling data using LZMA. Furthermore, to actually use these huge profiling outputs, we also now generate an SQLite 3 database. Yeah, and this leads me to the last slide I have, is that we now also do a big tooling rework. So we deprecated, for example, the very legacy thing that we called the preCICE tools. We now added specific executables for the subcommands, deprecated the preCICE profiling that you used during the course. We now have a separate package for this. We still keep the merge command because it's very handy on clusters. It is not really necessary, but this is still in preCICE itself. And this will also be removed in preCICE version 4. In general, you can use the new preCICE profiling package or use the preCICE CLI, which Felix Neuber will present tomorrow. Yeah. And with this, I say thank you.
Thanks a lot, Frédéric. We have time for maybe 1 or 2 questions, but before somebody asks one, so please raise your hand. I need to pass you the mic so that we can catch the question in the recording. So anybody has a question? Everything was very clear.
Okay. If not, you can always ask me after the talk.
Yeah.
Enough breaks.
Frédéric will be around. Let's thank him once more. Thanks a lot, Frédéric.